So welcome once again. Tonight we're going to talk about an alternative explanation to cosmological redshift. You might have heard of redshift relating to the expansion of the universe and the fact that it's accelerating and those kinds of things. But owing to what we've learned in the last 10 years or so about the Higgs field and Higgs bosons and the byproducts from them, I've got a postulation that's a new take on what could be the source of redshift. So later on, when somebody gets a Nobel Prize, you heard it here first. So, yep, it's going to be another one of those postulation things. The light bulb went off, and I said, I've got to do one on this. I'm not guaranteeing that this is the correct result, or that you can go, put your PhD on the line for this. But I'm saying that I think there's a connection here, and anything that's a postulation, I clearly identify with bold and italics. Anything that's an analogy where I'm trying to say, this is what it's kind of like, that's what I'm trying to say. You can see those things. So science is a cyclic process. So you start with some observation or question, and then you research it, you come up with a hypothesis, you do some observations, you do some tests to see if it matches your observation or your expectation. You analyze the data, and then you report your conclusions. If reality isn't as you predicted it, you throw out your postulation, you come up with something new, or you alter it to compensate for that. And that's the way science is supposed to dynamically work. So we start with photons. Photons have a stationary mass of 0, a charge of 0, and a spin of 1. What that means is that you cannot move photons around by a magnetic field. That's what the charge of 0 means. Has a mass of 0, which holds the standard particle physics science together. If photons had mass, some things would break. So it's got to be pretty rigidly 0, although photons do have momentum, which relates to their energy, not mass. And then spin of 1 means you can have photons that are in phase or out of phase with what you're imaging. So that's why you talk about like Polaroid filters to get photons in a different phase. But we declare photons can move no faster than the speed of light, or c. I'm not going to get down to the numerics of it. Just, there's a number for c. It's measured in meters or miles per second or whatever, but nothing travels faster than the speed of light. And nobody will ever give you a reason why that is the limit that it is. All they'll tell you is that is the limit, and they'll explain the limit. But why that's the limit is kind of ignore the man behind the curtain. So when you look at how photons interact with other materials, as photons pass into materials, there's a thing called the Snell, Descartes, Ebenshall law, or we just refer to it as Snell's law, where the material changes the bend of the light. It changes the speed the light's flowing through the material at. It's actually the transmissive speed. The speed of light in a vacuum is supposedly 1.0. The 1.0 is relative to the speed of light. So in a vacuum, it travels at the speed of light. As soon as you put it through a material that has a higher than 1.0 index of refraction, the speed of light slows down. Understand that? Not a problem with that. What you may not have realized is when the light leaves the material, it speeds back up again. Because if it didn't speed up and you really wanted to slow light down to nothing, you just use a stack of very thick glass plates and it gets slower and slower and slower and slower and slower, and then you wouldn't have light anymore. But it doesn't. You put in place a light panel, It goes at the speed of light, enters it, moves slower, and then as it exits, it speeds back up. Well, we refer to vacuum as a perfect vacuum. That is, it's a really, really, really good vacuum, as in there are no molecules of anything, there are no atoms. It's really devoid of everything, except it's not really devoid of everything based upon what we've learned in the last 10 years. There's this thing called the Higgs field, or vacuum energy, or quantum foam. These are a froth of Higgs particles that are everywhere. You can't see them. They have a charge of 0, which means they don't electrically or magnetically interact with anything. They're very high mass, about 125 giga electron volts. Now, it's a lot of electron volts, but compared to actually a volt, a battery kind of volt, it's small. But compared to other subatomic particles, that is a lot of electron volts. Spin of 0, which means it doesn't come in different flavors. It doesn't come with, in phase, out of phase. So this is the Higgs, and this has been proven to exist a couple of times by the Atlas detector at CERN. So the postulation I have is the speed of photons are constrained to c by the omnipresence of the Higgs field. Now, they've already done this with electrons. They've said the reason why electrons can't move faster than the speed of light is because of the Higgs field. So there's already analogous work of Higgs affecting the top speed of subatomic particles. I found a good analogy here. How many people are familiar with what oobleck is? If you take cornstarch and water and you mix it up into a vat, if you take your hand and you slowly plunge it into the oobleck, your hand goes in and comes back out. But if it's a long, rectangular, shallow vat, you can actually run across the top of the oobleck and not sink into it. So if you're high speed, the particles come together and stop you from penetrating the field. I believe Higgs is the same way. So if a photon wants to penetrate the Higgs field, it being, high energy and high speed, the Higgs field actually slows it down. And we'll get into how it slows it down in the next couple of slides. But just think of it as the Higgs field is kind of like the invisible oobleck for photons. This explains why photons cannot go any faster than the speed of light. They're too energetic. They get stopped by the Higgs field. Now the Higgs field, when it gets interacted with, produces Higgs bosons, Higgs particles. Here's something analogous. There is this thing that's proven exists out there called the magnetic permeability of free space. If you have an electrical charge, a magnetic field, that field will only grow out through space at a certain rate. And that rate is known as mu0. And it turns out that that's 4 pi times 10 to the minus 7th henries per meter. So there is a value that says a magnetic field will not propagate through free space any faster than this. They actually have curves for it that will tell you the flux of the magnetic field in Tesla or Gauss versus the magnetizing force you apply to it in Ørsted's. So you can put a lot of energy into it, but you notice how it curves over? It'll only propagate so fast before it just it tails out. And so I think the Higgs field does the same thing for photons. But as to whether or not the permeability of free space by magnetic fields is due to the Higgs, I'll leave that for somebody else to figure out. I'm just going to focus on the redshift and Higgs. So when a particle interacts with the Higgs field, it produces Higgs bosons. But Higgs bosons decay extremely fast. They will decay into other subatomic particles in 1.6 times 10 to the minus 22nd seconds. Minus 9 is a nanosecond. So we're talking very much small pieces of a second. So the Higgs boson itself doesn't last very long. What it decays into is the important thing here. It's been confirmed that a Higgs can decay into a bottom quark pair, a bottom antibottom pair, a tau and an anti-tau lepton pair, a pair of W bosons, a quadruple of muon leptons, or a photon pair. Now, you don't have to think about all the other ones, just think about the photon pair. So when a photon interacts with the Higgs field, one of the byproducts, not 100% of the time, a small percentage of the time, the end result when the decay occurs can be 2 photons. So a photon interacts with the Higgs field, the Higgs boson gets created, lasts for a very short period of time, and the end product of the decay is now 2 photons. 1 photon goes in, excites the Higgs decays, you get 2 photons out. Now, they've also predicted, but not yet confirmed, that you can get a top quark and an anti-top quark, a pair of gluons, a pair of Z bosons, 2 leptons, and a muon and anti-muon pair. But I don't care about those for 2 reasons. One is they're not yet confirmed. And the other thing is I'm interested in photons here, folks. So if I have a photon of a certain energy interacting with the Higgs field, producing 2 photons, it's kind of like when that light goes into the glass and the angle of the light changes, the index of refraction of the material changes it, and then when it comes out, it speeds back up. So you're talking about an interaction, the byproduct, and what's the end result. There's a bunch of other predictions that are deemed plausible, but they're lacking any predictive details, so I just crop those off. But most interested is the photon-photon pair. Here comes the funny bits. There is actually a Feynman diagram for the decay of a Higgs boson into 2 photons. And you start on the lower left with the Higgs, and you apply the energy from the Higgs, and it splits into 2 photons, and the photons have dissimilar energies. So you get 2 lambdas. So 1 Higgs in, 2 lambdas come out, and you have the mu and the tau lambda. You've got 2 different energies of photons. There is a thing called half
That is not lambda, that is ni. The little v is ni. N,
Yes.
like N, M, N.
Yes, you are correct. There's a thing called half harmonics and wavelength doubling. So as of 1990, they started working with nonlinear optics to see if they couldn't take in a photon and make it come out with a photon of a different wavelength. Not a different angle, not a different speed, but a different color, different wavelength. And they found out eventually that if you have 2 photons come in, they can go through a material, and the material will actually do doubling of the frequency. So you can take in an infrared photon pair and come out with a green photon out. Where this comes into play is your average green laser pointer. The laser produces infrared, a long wavelength. It goes through a particular kind of crystal, and then coming out of the crystal is 1 photon of a green wavelength. So it is possible for photons to go in, be changed, not come out as more or less photons, but come out as a photon of a different wavelength. When you have an exactly 50-50 split, this is called an optical parametric oscillator, and those are actually used in fiber optic communications. So this is real stuff. And if you remember the Feynman-Higgs boson decay diagram for 2 photons of dissimilar energies. There is the possibility for the split to be very unequal, not just 50-50, but really unequal, like 99.99999 versus 0.00001% difference. So you can have a photon that gets trimmed a little bit, and then the other photon that gets extensively cut back. So you can have a photon come in, interact with the Higgs, and now you've got a photon that goes out that's just a little bit longer wavelength than the original photon coming in, and the second photon going out can disappear completely into very long wavelength, either infrared or radio, and you won't even see it. It gets that much redder. Think about it this way. If it was really a 50-50 split and you had photons going in and then you had two photons coming out and they were both extended wavelength, they both got redder, the red would not only become darker, it would become brighter because now you have two of them, not one. But it isn't. What you get is not only does the wavelength get longer, as it gets longer, it gets darker. So you don't have two photons anymore, you only have one photon. And people might mention the conservation of energy. Where did the other photon go? The same way it goes in your green laser pointer. Your green laser pointer heats up. You use your green laser pointer, it gets hot. That's the infrared waste energy. So conservation of energy is just fine. We just take that other photon and throw it out as waste heat. Now this picture is actually the scatter diagram of a Higgs interaction from the Large Hadron Collider, from the Atlas instrument. But here's something to think about. If the reason why the speed of light has a limit of c is because of the existence of the Higgs field, and we know that if you interact with the Higgs field, you'll produce a Higgs boson that is short-lived. What if I were to find a way to create a lot of purposeful interactions with the Higgs field to create a lot of Higgs bosons, and then I put a beam of photons through that area of space? Would the light travel no faster than c? Because if the Higgs are gone and there's no interaction, it might travel faster than c. So that's the postulation here is if Higgs is holding back the speed of light to cap it at c, if you could diminish or disperse the Higgs field, would photons travel faster than c? I don't know whether the Higgs field is inexhaustible. So what if you knocked out a few Higgs bosons and you depleted the field a little bit? What is the density of the Higgs field? That's currently not known, but it's kind of assumed to be everywhere. So if you can disperse it a little bit, then maybe when light goes through that dispersed area, it won't be limited by c. Think of it this way. If I want to get into a vat of oobleck, I use a lot less force, moving a lot slower. How do I do that with photons? I use a very long wavelength, low energy beam of photons. If I were to put that into a Higgs field, would that consume a lot of the Higgs bosons, allowing me to put a follow-on beam of light through there, let's say ultraviolet, and have it go through? Don't know. I don't have the accelerator to work on that, but that's conjecture, as it says. So redshift in the expansion of the universe. Here's where it starts to meet up with reality. There's a thing called the Hubble constant, or H0, and it's currently agreed as being 69.8 kilometers per second per megaparsec. That's just an expansion rate. Hubble originally envisioned that it being 500 kilometers per second per megaparsec. And we've observed type 1a supernova and learned that, I think it's closer to 70. The 500 is obviously an inaccurate value. So even the guy that this is named after, the original number went from 500 to 70 because our observations improved. So the finer that we look at these things, the more accurate our actual constants will be. So we've calculated distance as things that we know the nature of them. If the light coming from them is redder, it means it's moving away from us at a speed of light. And we thought this to be a constant up until a guy named Guth came in and said, wait a minute, I'm seeing observations here that say the stuff that's farther away is getting farther away faster, which says that constant, not really a constant, it's more like a rate. So we know that photons shift towards red. We have confirmed that. We know that they can shift from UV down to visible. We know that they can shift from visible to infrared. And we also know that they can shift from infrared into radio or microwave. So the shifting is continuous regardless of the original energy level of the photon. How many people were aware of the fact that there's currently conflicting numbers as to how far the expansion has gone based upon the digital values we're getting back from observations? So if you were to look at the cosmic microwave background, you would see that it's 6 to 14 Kelvin. That's about 3 Kelvin cooler than it originally was. But if you were to look at Cepheids, the brightness of stars, you'll find that more like about 9 Kelvin, not 3 Kelvin. So there's a discrepancy of about 6 Kelvin between these two observational methods as to how far away the edge of the universe is going to be and how fast it's moving away from us. The other thing is not necessarily the frequency of the photons, but the compression of the separation of the photons. So they have multiple means of observing this, and they still come away with about a 6 Kelvin difference between the two observation methods. It doesn't sound like much, but over 13 billion years, it can add up. So particle generation cost. So when a photon interacts with the Higgs, and the Higgs produces a Higgs boson, and then the Higgs boson produces 2 photons, you can have one of the photons being at a slightly redder than it was coming in. So its wavelength is elongated, and the other one is so impacted that it gets lost as part of the generation cost to inefficiency and heat. So you can have one of them go through and have an end result, and the other one just, if you're not looking for it closely enough, just disappears. So all you see is it got redder. So if the interaction with the Higgs field is a reason for making photons redder, then the space-time expansion and dark energy aren't required. It's just the Higgs field's interactions that are causing photons to get redder as they propagate over more space. So not only is it not a space-time interaction, it's a Higgs field interaction, and it occurs not at a predictable rate, because not all Higgs boson decays are photon-photon. There's a bunch of other kinds. So it's only that particular quantity that will basically knock down the frequency or increase the wavelength of the photons. So I put it all into one slide here as the primary postulation is that photon redshift is due to photons interacting with the Higgs field, with each such interaction drawing a minuscule quantity of energy to emit decay resulting photons through dramatically unequal splitting, with lesser energy component being consumed to emit the short-lived Higgs bosons. Numerous such interactions over vast distance results in continual energy reduction and resultant longer wavelength for Higgs boson decay end product photons, without a requirement for space-time expansion or dark energy. Although considerable distance and considerable occurrences of Higgs fields interactions are required. This does not deny the expansion of the universe. It does not deny redshift and merely provides an alternative explanation for the observed redshift based upon the existence of the Higgs field and the two-photon dissimilar wavelength decay product of Higgs bosons. And if you say, well, this is a stake in the ground for science, and now we want to look at it from a different perspective and touch it up and come away with a different viewpoint, it's kind of like Einstein coming along behind Newton and saying, well, we're not really making gravity go away. We're just kind of explaining gravity a little better. This is the same sort of thing. It's not making redshift go away. It's just coming up with what we know about Higgs as the reason why it gets redder, and not simply because the universe is expanding physically. So if we know that the universe is expanding even faster as we get farther out, as it became earlier in the universe, then the same thing might be true with Higgs interactions. It might be that once a photon gets to a certain plateau of wavelength or frequency, that more interactions with the Higgs makes it even redder faster. Or it could be that the Higgs field is not uniform throughout the universe. It may be that the Higgs field is denser as you go farther out. Back when the universe first did its Big Bang, it may have been that Higgs field around the outside is actually denser and increases interactions, and therefore you're seeing it as it's getting redder faster. Now, if anybody wants to counter that postulation, I'd say bring it on. And I'm willing to accept any properly detailed critique of it. Go for it. That's my Rock'em Sock'em robots there on the right. Some might immediately raise doubt, absent the detailed critique, with phrases like, that's not how it works. Fine. If you understand the Higgs field, explain how the Higgs field doesn't have an interaction, because it does interact and it does produce photon pairs of output, and you can't have dissimilar values as explained by the Feynman diagram. So there's that. Pick a conservation of your choice, be it energy, mass, momentum. A photon is a closed system. Otherwise, photon recoil when it departs the atom at the speed of light from having been at zero to that velocity, that's a lot of momentum. So the atom should have recoiled, but it doesn't dramatically recoil. So skepticism is great. I have no problem with like, let me go look into that further and see if it makes sense. That's fine. But just sowing disbelief simply because it, shines a different light on long-held, stakes in the ground, so to speak, such as steady state universe. How long did we have that one before somebody said that doesn't quite work in the observations we're seeing? So for those people that have just got to see the math, here's my non-math major attempt at trying to explain it mathematically. So we have confirmations of the Hubble constant before it was deemed not a fixed constant, but an acceleration. That's definitely the case. Redshift is greater for older objects. This is where the constant accelerates. And that's fine. But if you have a photon, and if it's going to change its wavelength, how much did it change its wavelength by, if you know what the Hubble constant is? So if I take a photon and I say, I've got my redshift based upon the expansion of the universe, what is that reduction in electron volts of a particular photon as it propagates across the universe? And there's actually an article on that. And it turns out that it's 5.8 mega electron volts per megaparsec. I'm missing a slash there if somebody didn't notice that. So there's actually a number that's in this paper that will tell you how much that red light changes if you just work with the Hubble constant as a constant, not as acceleration. So we know that a Higgs boson has a particular mass. We know what the redshift is going to be per megaparsecs. So every megaparsec, we have to downshift the energy level of the resulting photons to lengthen their wavelength to make them redder. And so we know what that is. We know how far a parsec is. So the photon electron volt or redshifted amount is 1.778 times 10 to the minus 6 electron volts per light year. So now you have a number that you can plot as redshift. And that matches the Hubble constant. But this presumes that there's going to be far less than 60% of the Higgs boson decays, resulting in two photons of dissimilar wavelength. So the occurrence rate has got to be really low in order for you to achieve the Higgs constant reduction in energy, which lengthens it to make it redder. But what I thought that might be associated with is if the Higgs field is omnipresent and if the interaction starts at a small amount and then increases as you have more interactions over distance, then what else can we talk about that? And that is that you have one of two things occurring that actually increases the redshift, the accelerated expansion of the universe, as Guth pointed out. It's either that early on the Higgs field was denser, so you had more opportunity for expansion, or as photons get redder, the probability of interaction and reduction gets greater. So either the Higgs field is fixed for all time, or it was more early on and now it's less because it's expanding out. So we have two different approaches to how you get the Hubble constant from a constant to an acceleration. This is not even a postulation. This is not worthy of even conjecture. This is, if it turns out that the Higgs field constrains things to no faster than c, was the expansion rate of the Higgs field in the very early universe c? In other words, if the Higgs field is not a constant and it expanded, how fast did it expand? Did the Higgs field itself expand faster than c? And if that's the case, then fine. If the Higgs field did not expand as fast as c, then that means that photons on the lower density part of the Higgs field out towards the edge could actually travel faster than c because they weren't being slowed down by the Higgs field. So that's something that...
Not everything traveled faster than c because of inflation.
But what was the source of the inflation?
I don't know. I don't know. I'm only saying I thought everything traveled faster. I'm just looking at it ontologically, not epistemologically. I don't know why, but I thought everything did, and therefore Higgs did also.
Well, that's the question. We have no evidence of the expansion of Higgs. We just have evidence of the presence of Higgs. If Higgs could not expand fast as everything else was moving, and you had to wait for the Higgs to catch up, that would mean that the photons in the early universe could actually move faster than c. So that may give you a reason for that. Remember, this is just another way of looking at something that we already know and have observed and confirmed. So redshift still exists. It's only the explanation for celestial redshift that changes. Redshift would no longer be due to the expansion of space-time. It would be due to how many occurrences do photons interact with the Higgs field, producing photons of differential energies, with one of the photons being slightly redder as a result of the Higgs field interaction. Is the universe still expanding? Well, we're just measuring the wavelength. We don't know what the distance is. We're using what we know about existing stars and how red they are based upon the Doppler shift to say it must be expanding. But knowing what we know about the Higgs field, there may be another reason for it. So as I say, 6 of one, same as half a dozen of another. The redshift exists. It's only the rationale for why the redshift exists that might change. So the downside of this is, if this actually is proven, then the correlation between the age and distance of objects would be invalid. Yep, that's the case. And use of redshift as a basis for determining age would no longer be valid. Yep, that would be the case. Throughout the history of science, sometimes we get things what we think of as right, and then later on we learn that not so right. So, we have orbitals and celestial spheres and all kinds of things before these guys came along and said, maybe the sun doesn't go around the Earth. Or you have Eddington's prediction of the wavelengths, colors, and energies of stars, and then you have the HR diagram that says, nope, it's more like this. So the observations didn't change, just the explanation for what the observation's really telling us changes. Redshift would still be a basis for determining distance, but not the distance value. It just says things that are redder are farther away, but we can no longer use it as a means of determining age. We could use brightness of stars that we know their actual life cycle. They get dimmer or brighter as such. We could still use that. And Doppler shift would still work for determining wavelength shifting if things are actually moving, but the expanded acceleration of the universe would be more due to Higgs field interactions through open space than it would be to the expansion of the space itself. But maybe if we're looking for determining the age of things, we'll fall back on the stellar fuel consumption and metallicity of stars, which we have formulas for determining that. But then I thought this might finally explain the optical focus side effect that I've always seen. You think about it as, if I've got a refractor telescope and I want to see something relatively close, I've got to crank the back focus really far back to get the light to converge to my eyepiece. If I want to look slightly farther away, if instead of looking at something terrestrial, I'm looking at the moon, I can crank the scope in a ways. It's not that far away. Now, if I want to look at, let's say, Saturn, I got to crank it in some more. But if I want to look at the Orion Nebula, a little less. But if I want to look at a galaxy that is 1 million light years away, I still got to tweak the focus. And if the wavelength of light is altered by the omnipresent Higgs field, then that means that the light that I'm looking at increasing distance away from me is slightly redder. Now, if the two photons coming out of the interaction, one of them gets converted either to infrared or to radio, and the remaining light is just marginally moved to a redder wavelength, you won't even see it as being redder. But since you're looking through an optical telescope, anything that gets converted to radio frequency or infrared won't make it through the lens on the front of your telescope. So all you're seeing is the light that's coming through. I've got to move the focal point slightly because the angle changed. And if it's due to the fact that the light is just a tiny bit redder, then it's going to bend differently. So it may be that focus is actually the way of proving that that's what's going on here. But then I thought, well, wouldn't other things be affected by this as well? Other things that are also not charged particles, but particles that move around and supposedly move through things and don't get affected by them? Well, we currently have no explanation as to why neutrinos can go from lighter to heavier to lighter mass. There's a Nobel Prize that says, yep, neutrinos change flavors, and because they change flavors, there has to be an interaction, and the interaction results in neutrinos have mass. Don't have a charge, but they have a mass. So how would you add and subtract mass to a neutrino? Well, we already know from Higgs field interactions that Higgs is about 1% of the mass of all matter. So a Higgs field interaction, one of those byproducts can be it adds mass. It holds something in place by about 1%. The perception of it is mass. So it can increase the mass of something. Well, if this postulation holds true, you can also decrease the mass. So a Higgs interaction, depending upon the byproduct that you come away with, can actually increase mass or decrease mass. So now you have a mechanism that says, I can take neutrinos and I can shift them up or shift them down depending upon the resultant product of a Higgs field interaction. So it's just something to think about there. Now, the way you would prove this is you would start by looking at the neutrino flavor that you've produced. Neutrinos from reactors are electron neutrinos, so you know what they are. And then if they encounter Higgs, because you've got a Higgs interaction in your collider, you can tell what the expected end product would be. And then you use something like Boon at FermiLabs to measure the resultant neutrino flavor. And now you can actually see, did it go up? Did it go down? So that's why I want to see what's happening with Boon. This became a side effect, so to speak. This is a matter of observation. If you understand that particles can have this chirality known as spin, they can be left-handed or right-handed, and most of what we see are right-handed things, but we also know that neutrinos only have a left-handed spin. We haven't found any right-handed spin neutrinos, and we're assuming that, well, it's those sterile neutrinos that we haven't seen yet. Those must have the right-handed spin to keep everything symmetrical. Well, neutrinos don't have a charge. What if it's the fact that particles encounter the Higgs field and it raises or lowers their mass, which causes the change in spin? That would say that everything that has a spin is all left-handed. And if they happen to have a charge and they interact with something, that flips them to be right-handed. Right now, there's kind of a belief that everything has to have a right-handed spin, and it's only the lefties that we can't see. The lefties being those sterile neutrinos. But neutrinos don't have a charge. So maybe everything starts out as left-handed, and it's only the things that have a charge that get flipped to be right-handed, and that's why you get left and right-handed. Now, I'm at some point if I'm gonna do little GIF animations and such, I'm gonna have to look at a different way of presenting these slides, because these are actually two animations, a left curly and a right curly. They actually rotate. But anyway, it may be that left-handedness is normal, and it's only because your particle has a charge that allows it to be flipped to give you a right-handed particle. And that's why we don't see any right-handed neutrinos, because they have no interaction charge. Postulation is an aspect of the scientific method. Not all postulations will pan out, but postulation is what gets us from sticking with all that we currently know to uncovering what we have yet to learn and to correct invalid prior preconceptions or perceptions or misconceptions. It's how we went from Galileo to Newton to Einstein to quantum. If we stay at a particular plateau of known science, then it denies any future postulations, and so we're left with either science being replaced by dogma, blind faith, or the social malaise of groupthink. So as we observe deeply red, even radio microwave shifted celestial targets, and we have unexplainable ages of things, which if you look at some of the things that Dr. Becky has, some things have an age that would appear to be older than the universe. So take a look at it in a different light, given this explanation, and see if there are any legs. Or as an analogy, unless you believe it remains possible for Vader to not be Luke's father, Vader's claim to be Luke's father is initially conjecture. You follow it up with Obi-Wan's observations in science, and that's where you learn that that must be the case. But if you ignore Obi-Wan's observations, you introduce dogma to stay with what you've got. And therefore you get Luke's knee-jerk response of, that's impossible, with no explanation. I have to put the humor at the end. So you like the last bullet? I added that one. And then I have the usual. To let you know how much research I did, normally there would just be one slide full of links. 1, 2, 3, 4. So there was a lot of I've been working on this particular presentation for about 4 weeks.
Okay, so to begin with, you know, the postulation, the hypothesis that
I didn't have a hypothesis, just a postulation.
the field of physics says, you know, for what we've been searching so far, and that the Higgs field permeates everything.
Yes.
Just like the electron field permeates everything. So that's like the neutron field permeates everything. So there are many fields that permeates everything. So that's the first. Now, for you to observe a neutron or proton is easy because you can put like just few electron volts, and you can excite the electron field, the neutron field, or the proton field, and you can actually see the data very easily. That's why we discovered those particles first, because they are easy to be produced by the field that they permeate. Now, it took almost, 70 years for us to observe the Higgs particle, because even though the Higgs field permeates everything, for you to produce a particle, you need to input so much energy. You need to accelerate protons to the speed, like very close to the speed of light, like a third of the speed of light, in different directions, and collide a bunch of protons in those photographic machines that cost billions of dollars. And then you can see the trail of particles that come out of, and then they could finally produce a Higgs particle. What it means is that the Higgs field is there, but you need to input so much energy in that field for that field to finally bend and produce a particle that would be the Higgs field. That would be the Higgs particle, and then finally that was being proven to be the existence of the Higgs field, because we could observe a Higgs particle. But for you to actually interact with the Higgs field and produce a particle, you need to input a lot of energy. So even if the Higgs field permeates everywhere, photons that are traveling, that are coming out of stars, have so little energy that they would not be able to interact with the Higgs field to produce a Higgs particle. So that's not possible for you to actually produce Higgs and then to decay that in those two electrons that you're mentioning. I'm not saying that electrons might not interact with the Higgs field, but what I'm saying is that you cannot produce a Higgs particle in the regular space, because that is not enough energy. We are lucky to observe a Higgs particle colliding a bunch of protons in opposite directions in a tube, but we have to input so much energy. It took years and years. On the publications they talk that the Higgs particle is the God particle. No, it's not the God particle. What the scientists were saying is the goddamn particle, because it was so hard to produce. They first started to try to produce the particle when they had the linear colliders on FermiLab, and then they made the first cyclotron on CERN, and they tried to produce the Higgs, and it didn't work. They did the second one, it didn't work. That now they finally did, when they did the large circle, that they have enough acceleration, enough energy to actually produce that Higgs field. So in regular space, you don't have enough energy to actually produce a Higgs particle. That I'm not saying that your postulation has an idea or not. What I'm saying is that you cannot produce a Higgs in regular space with only photons of light. That's not possible. The other thing is that because we are in the ocean of the Higgs field, we observe all the other particles and all the virtual particles and everything that we observe as we are a fish inside a tank. So it's hard for you to observe something that if you are inside of it, for you to observe interaction or not. From our baseline that we are inside of the Higgs field, the photon doesn't interact at all with the Higgs field. And when we see particles interacting with the Higgs field, it causes them to have some mass. Not all the mass, like imagine a proton or a photon, that they are hadrons, those particles have quarks. So most of the mass are the interaction of the quarks and the gluons that produce some of the mass. But part of the mass of those heavy particles is caused by their interactions with the Higgs field. So they end up having a lot of mass because they interact with the Higgs field. And when we are looking at photons from the way we observing the interaction of photons being inside of a Higgs field and observing photons from our baseline, we don't see, like in the research, that is no interaction at all. And from what we observe from inside of the where we are, the photons are in the specific speed from the medium that we are, and that the limit speed that we are. I'm not saying that what you're saying is like it could be the Higgs field. It could be, but from what we observe, there is no interaction from photons from our point of view to be inside of the Higgs field. That's why we see the photons have no mass. Now, neutrinos have some very little mass, so they have a little interaction with the Higgs field. And then electrons, photons, protons, the stuff that we interact every day have lots of interactions with the Higgs fields. So you see those bodies being more massive. So that's what we observe. So in that case, what I want to say is that some of the measurement of the distance that will be annulled by you saying that photons have been interacting with the Higgs field, so that would annul the distance that we don't see it with that interaction. That would be one of those things. But the way we measure distance is not specific just with the cosmological redshift. When something explodes or when something have a high temperature, and we looked at the spectra of those objects, we can see ionizations. And depending on the ionizations, we can know the temperature of those objects. Knowing the temperature of the objects, we can extrapolate how much energy, what's the flux of energy coming out of those objects. And that flux of energy gives us the brightness. And with the brightness, we can calculate distance. So all the ways that we measure distance, including the redshift, is one more of the data that we put together to calculate distances. It's not specific, just the redshift of the light. You can see the ionizations of the chemical composition of those objects, and you know the temperature, and you know the flux and the brightness, and then you can also calculate ages and distance because of those temperatures and those specific elements that are being ionized. So in that case, your postulation for me is interesting. It could be that we don't see the interactions because we are the fish testing something inside of the water, so we cannot observe outside of it. So that's a really good idea. But from what we observe, there is no photon interaction with the Higgs field. But it might be just a point of view because we are inside of the Higgs field observing photons moving.
Are you done?
Yeah.
Good. I never said anything more than 1% of mass was from the Higgs field. Never more than 1%.
I didn't say that too.
You said it gets most of its mass from the Higgs field, and I said, no, that's not the case. I never said that.
Photons have no mass.
No, I'm not talking about photons. I'm talking about protons.
Protons get some of their mass from the Higgs field.
I said not more than 1%. How much?
I didn't even pay attention to that. I didn't say anything.
Second thing is, you cannot actually detect a Higgs boson. It's impossible to detect it. All you can detect is the byproducts of it. They have detected photon-photon byproducts from a Higgs particle.
In colliders.
Yeah. So if that's one of the numerous byproducts, then it can exist in nature. However,
Higgs boson cannot exist in nature. It only if you have huge collision, maybe a supernova or like near black holes.
How fast do electrons move in free space?
Very close to the speed of light, depending if they come out.
Why
from
not the speed of light?
supernova.
Why not the speed of light?
Because they have mass.
They have mass.
Where do they get the mass from?
The Higgs field.
Yeah, but you're not producing Higgs particles. You can interact with the Higgs field. We are interacting right now with the Higgs field, right now at this moment.
Yeah.
But we are not producing Higgs particles.
You're saying you're interacting with the Higgs field, yet you're not producing any Higgs particles.
No. You need huge energy amounts for you to produce a Higgs particle.
How would you know if you were or not?
You cannot, because there is no decay. You can, if you would
How would
not
you
need.
know? How would you know?
Monroe, all you needed to do to capture a Higgs particle, if it was that case, was a cloud chamber. You would be, detecting Higgs particles if it was that easy.
Nope, because the Higgs particle doesn't even last a femtosecond.
But you would see the decay of the particles.
No, you wouldn't. It doesn't last long enough.
I mean, the decay left over of those particles they're forming, you can see only in colliders. But if you could easily produce a Higgs particle, you would not need a large hadron collider.
Higgs particles are happening all the time.
Nope. The Higgs field permeates everything, but for you to actually give enough energy to produce a particle, you need a lot of energy. Now, I'm not saying that there is no particle interaction whatsoever with the Higgs field in the case of photons, but what we observe from the inside of our medians, there is no interaction of photons with the Higgs particle. Photons don't interact with the Higgs particle. Photons don't interact, with it. Yeah, there is no interaction. What are you pointing out there? I don't see it.
So where are you getting a pair of photons from?
Quantum fluctuations.
No, you're getting them from
they are not
field.
the quantum fluctuations. So when you have a pair of particles, they're the antiparticles and the particles.
No,
They are
these are not
created
antiparticles.
and then sometimes when they annihilate themselves, then they produce photons.
These are not antiparticles. These are both photons. They're confirmed. You can have photon-photon results from Higgs interactions.
Sure, sure. But for you to have a decaying Higgs particle, you need to input a lot of energy. That is a many Feynman diagrams of those collisions and those particles. They have the Feynman, and then there's always photons coming out of them.
You mean that?
Yeah. So
Yeah.
that is not just that one. There's a bunch more. This is one of them.
Exactly. This is one of them, which means every interaction doesn't result in two photons.
Yes, they have photons being emitted.
Yeah, but not always.
After they input the energy, not always, but it depends. I don't remember all the Feynman diagrams for Higgs boson. I just know the first ones, the ones that I pay attention when they just discovered. So I only remember 3 of them, but there is way much more because they found heavier Higgs boson particles. Like they're getting more and more energy, and they are trying to get like a few more different kinds of Higgs boson. But there are many of the decay diagrams that shows photons coming out. Now, the photons do not, they are the result of the decaying, of the cycle of the decaying. They are not the specific interaction with the Higgs boson. Photons don't interact directly. They are a result of the interaction.
Do particle accelerators accelerate photons?
No, not that I know.
Why not?
Never heard one that does.
Why not?
Because they don't have mass, and massless particles travel at the speed of light in a vacuum, so they can't be accelerated or decelerated. That's why there's a redshift.
They don't have mass to collide to produce something else.
Is manifested in a change in frequency, not velocity.
Exactly.
Okay, I just asked you both a stupid negative question purposefully.
Okay.
What I was trying to get at was, if you cannot control the direction of photons with fields, how would you ever know that it's impossible to have an interaction?
So far, we haven't seen one that I have read. No.
Okay, then I advise you to read up on photon-photon collisions.
Okay, that's interesting. Okay.
Because they've been observed. They've been confirmed.
And what happens when they collide?
How is it possible for two massless particles that don't have a controllable field direction to interact?
I don't know. That one is not part of the stuff that I study.
So, yeah.
But I have basic physics, so it's like, I of course.
Yes.
But
so
what I'm telling you
look
is
up
that
photon-photon collisions.
And what do they produce? What is the Feynman diagram? I don't understand that one. Totally.
You don't have to understand it right now, but you can go do research on it and find out.
Yes.
Yeah.
But do you know?
Photons.
Yeah, but higher energy, lower energy, what happens?
I'd say go read about it.
Okay.
But forever we thought,
yeah, sure,
it's impossible for photons to collide with other photons.
I'm not saying that. I'm saying that I don't know.
No, I'm saying general science said it's impossible for photons to interact with other photons because they don't have mass.
Yeah.
But they do have momentum.
Sure, because they have energy.
Yeah. So if it's possible and confirmed that photon-photon collisions exist, then photons can collide with things that normally wouldn't happen.
Yeah, but only have interactions when it collides with something that has mass. Like a photon colliding with something that has mass. It
Nope,
produces
nope,
heat,
nope,
it
nope,
produces
nope, nope,
momentum.
nope, nope, nope. This is a photon colliding with a photon.
Okay. I haven't read anything about that.
You can.
Yeah, okay. That's just,
Photon,
but
photon
you know,
collision.
going into that case, that what you're saying, for now, for what I've read, for what I learned about the Higgs field, there is no way that you can produce it like in the regular space-time where you have the Higgs field. You cannot produce Higgs particles, and that is not the K of more than one photon. And this is not the mechanism.
Okay,
That I am almost sure.
stop right there. Here's a list that says you can have a photon-photon pair as a decay result of a Higgs boson.
Yes.
Yeah, so it's not an anti-photon.
It is what? A result,
Yes, it is a result.
not an interaction.
How did you
It's
get
the
the result?
result of the interaction.
How did you get the
But
result if you had no interaction?
yeah, how you get the result? You get uh, different directions circulating protons, heavy mass objects colliding and being blown to the smithereens, and that creates so much energy that produces a Higgs particle. There are Higgs particles that's like less than very small fractions of seconds. Then what they actually measure in the big machines, the big photographic cameras that has, thousands of terabytes of information being captured at that time, they are not capturing exactly the Higgs boson, but the decay of the Higgs boson. And some of
You're
that
saying
decays are
something I've already
photons.
explained, and it's sitting right in front of you.
Sure, what I'm telling you is that photons will not produce Higgs bosons. It normally uses some kind of a heavy particle. The ones that I know is the W boson, or one is bottom and one is the tau. I've seen the Feynman diagram. I haven't seen the Feynman diagram that doesn't has, other than the pair of photons, but there is a W boson there, a decay. But that is a change on the W boson. It
Yep.
could be a positive or negative. It's actually
Negative.
and
Yeah,
so
it's not
it
positive, it's only
changes the
negative.
decay of the W boson. That's a heavy particle, and then in the result, two photons are coming out.
Yes.
So that is a change in a massive particle. A W boson is very massive. It's the one that the interactions, the the W particles are the ones that rule the radioactivity. So you have like the changes in protons to neutrons, and coming out photons of gamma rays and changing the particle. You have a whole full head of the helium coming out. That would be an alpha decay. Or you can have electrons coming out, and you would have a beta decay. Or you have photons coming out in gamma rays. So that will be ruled by the W boson.
But nonetheless, does this diagram show that the final decay product is two photons?
Yeah, but can you see the cycle of the W boson and the protons changing?
I don't understand the cycle.
Okay.
That's why I'm asking, is it correct that the two end products are exclusively two photons? Because if they aren't, then what I'm saying isn't correct.
Okay,
So,
the Higgs is 128 giga-electron volts. The W boson is 80 giga-electron volts. If you're going to conserve the energy of the original particle coming in, then you subtract the W boson, and what you have left, the sum of the two photons, is the remaining energy from the decay. The only thing that exists after the decay products occur is the two photons, because they're long-lived.
Yeah, that was
the
the
Higgs,
leftover of destroying protons.
the Higgs decays, you get a W minus out of it. The W minus decays, you get 2 photons out of it of dissimilar wavelengths.
You
Oh,
have
Yes,
a
okay.
decay
it
there.
goes through
Changing
its
that
own
to.
Feynman diagram. So it
Oh, okay.
takes its
Sorry.
energy
Sorry.
share out of the Higgs so that the maximum wavelength you can get out of the 2 photons is reduced by the energy level of the W. So if you take the energy coming out from the 2 photons as K1 and K2, you have to sum that up as the original Higgs is K1 plus K2. And then as it circles back around, you can see it cycling minus K2, minus K1, and then you come back to the proton.
Thank you. Okay, I kind of got that now. Thank you. Thank you.
The end product to explain here is Higgs goes in, 2 photons come out. The 2 photons have different wavelengths. That's all you're supposed to get from this diagram.
But because you give collision, you actually gave the energy. The energy goes in, produce the particles, and then the particle decay, and you have the leftover decay for you to understand what particle was produced. But you know what energy you input in the system, and you know what you should come out in energy, and you know the mass that you input in the system. You know that the mass should be constant, it should just transform in something else. And then you can calculate the results of that interaction so fast that you can kind of figure out the Feynman diagrams of what kind of particles were created and what kind of energy came out of it. But you know the initial mass and you know the initial energy that you input in the system. So you observe with that collision what kind of mass particles came out and what kind of energy came out of it. I don't know if that made understood.
I finally expanded my phone and expanded it, and now I can see the arrows on the interaction that it's a cycle. Them arrows are important.
Well, the Higgs is a collection of energy K1, K2, and the intermediate interaction is the W boson, and you can see it cycling around K1 to K2 back to a proton, but you subtract out the energy of the W boson from the Higgs, and what you have left over is the K1,
Proton back
K2,
again.
and the K1, K2 are the energy levels of the photons that come out of the result. So an interaction occurs, you get 2 photons out.
And what is cool is that for you to describe all those interactions in the specific equations that I cannot even read is basic 5 pages of equations that hits the head of any doctor degree student kind of thing. And now Feynman makes a diagram that people like us who have basic understanding of physics can understand the interaction. Isn't that even more amazing?
They should give him a Nobel Prize.
Like those diagrams are genius because it translates something that is so freaking complex and something simple that we can explain to people. It is like for me, from all these presentations, like I'm Feynman fangirl.
I obviously appreciate his work. Otherwise, I wouldn't have included the references to him and the diagram in what I'm presenting. So the number of times that a photon can have its wavelength elongated or its energy reduced over a distance of light years such that you get a very small change in the electron volt level. And I've got that number for you. And it is 1.778 times 10 to the minus 6 electron volts per light year. So if you were to take a photon and propagate it over a distance of 1 light year, the energy level of that photon would drop by that amount. And if it drops by that amount in 1 light year, and that happens to pretty much be dead on with the Hubble constant, then somehow, in order to get redder, that photon had to reduce energy.
Where is the paragraph that you just read?
Photon EV reduced, red shifted by 1.778 times 10 to the minus 6 electron volts per light year.
Okay.
So if I have a photon and it traverses a light year, the wavelength difference, under the presumption that things get redshifted, is that amount. And that amount maps onto the Hubble constant. Now, if you want to reduce that by that amount per light year, you have to have interactions with something that is more energetic, to take it down a notch, to re-emit the photon at a longer wavelength, at a lower energy level.
Yeah, and for right now, what they're teaching schools, especially my level, is that because the space-time is expanding, quantum fluctuations causing the expansion, and then because of that stretch of space-time is actually stretching the wavelength that we are observing, and that's what we see the loss of electron volt energy. But as Monroe says, we are not sure if that's what is happening.
Right, and that's what I'm pointing out here, is it doesn't make redshift go away. Redshift is a thing. It just gives you an alternate explanation as to why redshift is occurring. Redshift can either occur because the wavelength is stretching because space is expanding, or it could be that the photons that you're observing are getting their wavelength elongated by having their energy reduced. So once a photon is shifted from visible to infrared to microwave, we can no longer see it.
We can
Because
see with radio.
Well,
No. When it goes from infrared to radio, it goes to microwave. And the next step down from there would be longer wave. And we have no space telescopes that operate in the longer wave spectra. How far redshifted can photons go?
We don't know.
Exactly, because we have no instruments to measure it.
I know that you used to, I'm not sure if it's still correct, that you used to need a antenna that was a multiple of the length of the
wavelength.
Of the wavelength.
Yep.
Is that still true, or
Yep.
for example, when you're okay, so that's a law of physics. So when you have your iPhone or your tablet, and you're getting, is that how is there a tiny little wire inside that's doing that or something?
No,
How
there are fractal antennas that are used in cell phones nowadays, and the fractal antenna is a small multiplier of the actual wavelength. And what we do is we gather the data, run it through a dedicated microprocessor to stitch together the samples of data to actually resurrect the waveform. So we chop it up and then we reassemble it. We don't do that with very long wavelengths because there's not enough energy in them. So if you want to receive, let's say, shortwave AM down below, let's say 100 kilohertz, you're back to putting a very long wire outside. And if you look at radio communications arrays that do very long wave amplitude communication, which still exists, they're just very long wires outdoors. So if you wanted to have an instrument that could receive the even further downshifted than infrared wavelengths from space, you would have to put an enormous radio telescope out into space, and we don't build those. We built the James Webb Space Telescope, and it has a certain measure of aperture, But even that runs short because it doesn't go to the deep infrared. It only goes from the shorter to the mid infrared. So even the James Webb Space Telescope has a limitation on how red it can see.
Even though it's the largest one that we have.
Yes. And there is even larger ones that are in the works that are planned that we just need a few billion more dollars and maybe another decade.
Yeah.
So never, I mean, you can postulate the things beyond what your instruments can see, but never presume that something doesn't exist simply because you haven't got an instrument that can see it. Or infrared can't exist because we don't have anything that detects it. Or ultraviolet can't exist because we don't have anything that detects it.
I'm detecting infrared right now at this moment.
Yes,
Because I
because
have
it's-
my laptop. I have my laptop in my leg.
Okay, we're past the bewitching hour. Let me get to the last slide again here. That way I can close out the video. Okay.
Oh,
Any more comments or questions before I stop sharing?
ah,
I know, enough for one night.
yeah, definitely. Well, was good to hear you. Thank you.
Okay. So let's stop
Good
sharing.
night.
Good night, everyone.
Bye.
Thank you.